Okay, so once more, we've got this reversible reaction. A goes to B and B goes to A. We are given the kinetic rate constants fully described, pre-exponential factors, and the activation energy. And we want to operate the CSTR and the PFR. So it mentions we've got those two in series. We want to operate them at as high a rate as possible. And it mentions a couple of things. The reaction stays 10 Kelvin short of the equilibrium temperature. It also mentions that we are fed, so the reactor train is fed by component A. We are given the heat capacity of A and the inlet temperature and the inlet flow rate. And let's see, and then it says refer to the figure. Well, what I want to do first is show how to get the figure. So we won't use the figure that's mentioned there. We're going to create a figure for ourselves. So towards that, I've just started up Python here. So let's just do it from scratch. Let's make a new notebook. And what we want to do is create the plot for the reaction rate. And so we want to plot the reaction rate as it varies with temperature. So let's just write first what the reaction rate looks like. So if we write it in terms of the rate of consumption of component A, then A is consumed in the forward reaction, so K1 times Ca, or in the problem it's given to us as Kf. And so we can say KFCA, and then A is not consumed, it's produced in the second reaction. So that's going to be a minus KRCB. And then, of course, we know we can write that as Ca naught. So this is Ca naught, and then 1 minus Xa. And then Cb is equal to Ca naught times X. Right, so A produces B. So whatever of A is converted to B. So Cb equals Ca naught X, right? And I should say that's Xa. And then what we can do next is group out for Xa. Actually, let's group out for Ca naught first. So we can, okay, let's do it as a new one. So let's group out for Ca naught. So Ra over Ca naught. So we get rid of the Ca naughts over here. And the next thing we can do is group out for Xa. So we're going to, instead of grouping for Kf here, we're going to say Xa, or let's say minus Xa. And we can see in the first term here, it's Kf. So this is going to be Kf. And then in the second term here, it's Kr. So that's Kr. Right? And so that's, those are the X terms, and we still have an additional Kf over here. So it's a Kf. Okay, so just have a quick check. Does everything look right? So we've extracted the Kf, and then we've split out a minus Xa. So we've got a Kf and a Kr like that. Okay, and then let's make Xa the subject of the formula. And I'll explain why we are doing that just now. So first off, when we take this Kf across, then we'll have a minus Kf here. And then instead of keeping these minuses, I'm just going to write those all as pluses. And then here, we want this in terms of Xa. So we'll just divide both sides by that. So Kf like that. Okay, and that's basically it. So Xa equals this stuff. Okay, and actually what we somewhat prefer to do is write this in terms of consumption of A. So this RA is, of course, the rate of formation of A. So if we want this more in terms of consumption, if we want to think about RA as a positive, if we want to define RA as the consumption, then we can use a minus sign there. But anyway, let's just leave it like that for now and see how we go. So this is the conversion of A if the reaction is RA in the reactor. And let's see now how that's going to look on a so-called isorate plot. So a couple of things to note here is that these rate constants are all temperature functions, right? So we have a temperature dependence here. And this rate, we know rate changes with temperature. But for right now, we are going to view this rate as a fixed number. So what we want to do is investigate this plane. Let's just sketch a plane here. So we know that on X and T, that we can draw the conversion and the temperature, and we are interested, let's say we are talking for now about the CSTR. So in the CSTR, we know that there's a certain temperature, so we can define the temperature in the reactor, so T here, and then for some temperature, there is some conversion. And we know that we have the energy balance, right? So from the energy balance, which is mentioned in the question, so here's the energy balance, remember, gave us this relationship between X and T. So X and T are related to each other. And that, again, that came from the energy balance, whereas this is different. This is simply stating the reaction rate in terms of the individual reactions, right? So that's our net reaction rate. Now, this net reaction rate obviously does depend on temperature, especially through these kinetic rate constants, and it also depends on the conversion. So what we want to do now is, in a way, investigate nature, right? This is nature. This nature determines what the reaction rate is going to be if your current concentrations are these values and your current temperatures are driving these values. So this is what nature is doing. This is what we are doing as engineers, right? If you think about this equation up here, this is how our reactor is operating. It's chugging along when we apply a different temperature, or if we've accomplished a certain conversion, then that's how X and T are related. So this is different to this. This is in the reactor, the nature that's going on, the reaction rate that's being accomplished. That's what's determined by nature. So we would like to, in a way, investigate nature and see what values are possible there. We'd like to know what relationship, according to nature, what's the relationship between X and T? So far, we have simply taken the statement of the net reaction rate, and we found a relationship between X and T. So let's plot that for this question. So in this question, we are given these constants. So let's go ahead and in our code here, let's plot out X as a function of T. So just quickly, okay, oops. That's okay. And then let's look at temperatures in the range 200 to 800 Kelvin, right? Typical reactor temperatures. And we want to determine K1 or Kf. So in the question, we've defined the forward rate constant. So it's 30 times e to the minus 28,000. So 30 times x minus 28,000 divided by r divided by t. And let's define the universal gas constant 8.314. And let's do KR in the same way. So KR equals, and here's 1,280, and the activation energy here is 39526. 39526. Okay. So forward and reverse constants are defined. And let's just set an arbitrary inlet concentration of 1, right? And let's see our equation. So that's all defined. Only RA is not defined, right? But let's just fix a value for RA. So let's say RA equals 0. All right. So we're going to look here at x as a function of t. So we can say x equals, and according to our development here, it's going to be the forward constant plus RA over CA naught. So we can say the forward constant, so KF plus RA over CA naught divided by KF plus KR, okay? And so let's just go ahead and plot that. Okay, so that's our equilibrium line, right? We've specified an RA value of 0. So the net rate, when it's 0, looks like this. It's along all these points, the rate is 0. So that's something for us to kind of acknowledge, that this is a special choice. There's nothing automatic about this. We are choosing to look at, on our xt plane. So this is the xt plane, of course. So there's x, sorry, there's t and there's x, right? And we could pick any point on this plane. So if we pick a point here, there's a certain reaction rate for that conversion. If we pick some other point, there's another reaction rate for that. So we have determined now which combinations of x and t give us an RA of 0, right? So all points along this line, for all combinations of x and t along this line, RA equals 0. So that's the equilibrium line. And the thing we said last time was that if we are trying to accomplish something, if we are trying to consume A to produce B, then this is the line we want to stay away from, right? In effect, nothing is happening here. There's no net consumption of A along this line. So we want to stay away from this equilibrium condition. Now, the nice thing about what we've done here is we are free now to consider other values for RA. So let's say we want to consume A, so we want a nice negative number. So let's just specify a -1, for example. So let's see what that gives us. And we are out of range down here. So what I want to do is set some limits for my plotting. So to do that, all I need to do is choose the axis. So we can say axis. So axis equals ELT get current axes, and then set our limits. So set y limits between 0 and 1. Okay. And when we do that, we get nothing. That's surprising. Let's see. So maybe this -1 is too small a value. So let's say minus. Okay, so now we start to see something. So we can see now that we get a different contour here. So when we set a conversion for component A, we get a different contour, a different combination of X and T. Okay, let's see, there's some chat messages. Okay, tutorial 2, submission to tutorial 2, not submission. Yeah, so I know I haven't sent any Publons recently because the material we were doing, the Publons don't work so well on that. We are working on making on adding to the functionality so it will support these other types of questions. So there'll be more Publon type questions. So for the time being, you'll find in the Dropbox folder tutorial 4. So that's the one to work on. We'll be adding more Publons later. And then another question, for RA, do we always have to assume it or will we be given it sometimes? So yeah, the question is, why did you go and choose this value for R equals 0? So at the moment, we are not answering any kind of question here. At the moment, we are just thinking about trying to understand the situation. So what we have available so far is we've got a nice function for Kf and Kr, right? So that's information that's been given. So we are saying now, well, let's just think about the possible reaction rates. So we haven't as yet said we are trying to do anything. We are just looking at the plane and thinking about different regions. And that's going to help us answer the question later, obviously. But for right now, we are just arbitrarily choosing R equals 0. Well, this one is not so arbitrary. R equals 0 is important. It tells us a region to avoid. And then I chose this value just arbitrarily again, just because it gives me something to see. If I choose too high a rate, like when I chose -1, then it looks like -1 is just not possible at these temperatures. So there might be some other temperature. Maybe let's look at some crazy temperatures, maybe -2000 degrees and going up to 2000. So you see at some very low values below 0 Kelvin, not really possible. You get some, you see some action, and then beyond 1000 degrees, you see some action. But that's not in the region that we are interested in. So in the real world, 200 Kelvin to 800 Kelvin or 900 Kelvin, that's more reasonable. So in practical engineering terms, we can't really accomplish this rate. We do seem able to get to this rate, right? So we are just exploring the plane there. Sure, Andile. Okay, so we drew the first one, and then the second one we drew looks like something around here. And then let's try another one. Let's try a smaller value, 0.5. So this one has shifted a bit more. So this one looks, that's probably somewhere like there. So we are looking at different contours, and along these contours, along these lines, we have a fixed reaction rate. In other words, these are the combinations of X and T values where we have a fixed reaction rate. And the reaction rate in this case is this value. So we call these iso rate lines, right? Iso rate means it's the same rate. So along these lines, along this line, it's the same rate, which is this value. So this is starting to give us some information about the plane. And to see that a bit better, let's do this again. But let's run a loop. Let's plot multiple such lines. So I've just copied that there, and now let's set a group of RA values. So let's make RAV be or maybe log spaced, right? Let's try log space. Let's go from -8 to -1. And let's use, let's just use 5 for the time being. So we're going to run a loop. So we say for RA in RAB, we will recalculate X right? So we recalculate X for each of these RA values, and then we plot all that. And we still want to set the limits. So let's see what that gives us. Okay, so we can see lines going in this direction. And by the way, there's still the equilibrium line here, but we are getting RA values which are positive, right? By the way, just let's print this print RAV, and you can see when you set a log space, it starts at -8. So this is 10 to the -8. And then the last value is 10 to the -1, which is 0.1. So there's 0.1. So you are starting with very small numbers and logarithmically small, and it's increasing like that. So, but these are all positive, right? This is for the rate of production of A. So that's not really what we want. So let's just say minus that. So now we are looking in terms of the consumption of component A. And we can see then multiple isorate lines here. We can see something that looks like the equilibrium line. And okay, and we can see that we seem to have the high rate regions down here and the low rate regions up here. So we would like to operate down here, or rather we like the reaction rates down here, but that's in a very small region. And we are starting out, I think in the question it says 300 Kelvin. So we start 300 Kelvin. And so our reactor starts here, and because it's pure A initially, this is the right point, right? So it's pure A, that means X is 0, and we are at 300 Kelvin. So we are starting at this point here. And so we then have to think about how that reactor is going to progress through the space. So right now, we've just looked at what nature does. So if you like, these rates are available. This is the plane of rates that nature is showing to us. It's showing us there is a very low rate region and there are high rate regions. And so we can think about picking points and estimating rates. So for example, if I pick a point here, maybe midway between this rate line and this rate line, then I can see this rate line that's on the order of minus 0.1. And then this red line is on the order of minus 1.8 times 10 to the -3. So if I logarithmically average it here, then I can get some estimate for the reaction rate there. Okay, so that's just the plane of rates. We can also say, well, what about this big empty space over here? Is nothing happening there? And that's not true. It's just that on this side of the line, component A is being consumed. And then we assume up here, component A is being produced. And we can see that directly if we just go ahead and take another set of values. Just getting rid of that. And let's call it RAV2. And so that will be rates in the upper region above the 0 value. And so here let's add to our plots. Let's just make this X2, and this will be RAV2. Okay, that's not really, I need to run a separate loop for this. So let's do that, RAV2, and then let's just call that X also. So then we just add to our plots that way. Right, so you can see in this region, A is being produced, and down here, A is being consumed. It's not that you can tell that by just looking at this plot, but if you look at the values behind these isorate lines, here, RA is positive, and here RA is negative. So that means Ra is consumed here and is produced here, right? And so that's the plane that we have. So we want now to navigate this plane. We want to move around on this plane, and we want to accomplish a good reaction rate and get a good conversion and all of that. So let's start looking at how to plot our reactor line. So I'm just going to copy that plot there. And now we have our energy balance. So we did say that our energy balance is what determines our the operation in the reactor itself. So let's just write the equation over here. So we've got, so here we've got XA equals, and it's going to be sum over theta, the inlet flow ratio, times the heat capacity, divided by the heat of reaction, and it's minus heat of reaction, right? So go back and have a look at our energy balance and you'll see all this. And then it's T minus T in. If you go back and look at the energy balance, you'll find that we did also have a Q term. We did have the heat added by temperature difference. So that was a term we had before. But what we are doing now is just saying, well, what if we are not adding heat or removing heat from the reactor? So instead of saying that we have a heating coil or a cooling jacket or something like that, so instead of saying we have that, we are just going to assume we are not doing anything like that. And it's just simply flow through this reactor, right? So if we are not heating or cooling that reactor, then we don't have to worry about that Q term. And so that's the equation that applies, right? So that's our energy balance. So let's go ahead and plot this out now. So in the numerator, we can see the theta I CPI. And if we think about what the problem says, we have pure A initially. So we would like to operate, the fresh stream contains just component A. So only component A is there. So that means we have a theta A of 1. Maybe let's write it strictly. So normally we would write this. We would write theta A times CPA plus theta E times CEB. So that's what we would normally do. But we have pure A. That means theta A is 1 and theta B is 0. So this thing is simply CPA. This whole thing reduces to nothing but CPA. So that's the numerator, and we are given a value for CPA. Now, heat of reaction, we can also get, so delta HR. If you think about what we did last time with the Fantoff equation, we eventually saw that the heat of reaction could be estimated simply as the difference E1 minus E2. And if you look at what we have here, we do have a hidden E1 and E2, right? The forward activation energy and the reverse activation energy. So we seem to have everything we need for this part of the equation. So we can say here, and I'm going to say it kind of more easily as dx dt equals, and it turns out it's as easy as CPA divided by, and down here we've got minus E1 minus E2. Right, so let's add that to our calculation list. So in here, we're going to say dx dt equals, and then it's CPA. And I prefer to keep my variables like this. Then it's divided by minus E1 minus E2. So I always try to keep my variables with numbers up here. So we're going to say CPA equals, and in the problem, we are given the heat capacity for A as 28.8, just check units, joules per moles per Kelvin. So everything's in SI units. So that's fine. So 28.82. And then E1, and it doesn't really show here what units are being used, but if we assume these are SI units, then E1 is 28,000, and E2 is 39526, 39526. Okay, and so there's our dx dt, and we might want to just plot it or print it just out of interest. So that's the value. And we can see it's a positive number. So dx dt, it's sloping in this direction. It's going to point like that. And now let's choose some values. So let's say we are going to go, so T in the reactor. So we are choosing some values in the reactor. And let's go from, we know we start at 300 Kelvin, and let's just choose 600 Kelvin. So that's T in the reactor. And then going back to our equation here, we've got that what we actually want is this. So if we rewrite it using what we've got over here, then this is XA equals dx dt times T minus T in. So we can write here X equals dx dt times T in the reactor minus T in, okay? And that should be enough for us to just say PLT dot plot, and it's T by X. Oops, something's off. T in is not defined, okay? So T in equals 300 Kelvin. And let's always try and get rid of numbers here. So T in, and in fact, this T, let's call this T end. Let's try and keep all the numbers together here so that it's nice and soft coded. And if we want to change our simulation, we just go to one place and make the change there. So yeah, okay. So why does it go to 900, by the way? 600 T and TR. Oh, I'm plotting against the wrong T. I need to plot against TR, right? Okay. So that seems to be our line. It started at 300, ended at 600, and then X is changing according to our equation. So X changes in this way. So our operating line is pointing up like this, right? It started at 300, and then the system moves up in this direction. And the interesting thing about this is that we are going through different reaction rates here, right? Remember, these curved lines, that's what nature does. And of course, we generated it all. It's not like there's something mysterious, right? You see, when we say this, then we are already specifying that we know everything nature is doing in this reaction. So we've fully quantified how nature operates because someone has gone and done the work of measuring these kinetic rate constants dependence on temperature. So all the work has been done for us. And that has given us the luxury of being able to say everything about how nature behaves in that region. And then on top of that, we are able to say that, well, if we start our reaction here, if we specify an initial temperature and we let the system react, it's going to move like this. And if we think about this, there is an issue with this. Well, not actually. It's telling us, if we think about what happens here, the system will start at that, and then after some time, it will convert further. So our X will slowly go up. So as X goes up, T also goes up. So according to the way this line has turned out, right, from our energy balance, it's telling us that if we release the system here, it will rise in conversion and temperature. But we can see that we are getting closer and closer to the equilibrium point. That means, although we drew this line so easily like this, if we were to actually draw how do we say, if we were to actually draw how the conversion is changing with time, right? Not with temperature, but with time, we expect it's going to do this. It's going to slow down, right? So the reaction rate becomes very, very low around this region. So we are going to be limited to this value of around 0.32 maybe. So 0.32. So that's equilibrium. Values out here still do exist, but in this region, we have on balance a movement down towards equilibrium. So as we said before, nature is always pushing us towards equilibrium. So the only way we can get up here is if we use component B. If we feed component B into the reactor, then we'll get an artificially high conversion. We'll see a lot of B in the reactor and say, oh, so conversion is that value. But that will then cause the reverse reaction rate to be greater than the forward reaction rate, and then the system will start to come down like that. So if we start at some higher conversion, it's going to do this. Right, so the equilibrium point is attracting both sides of this. Okay, any questions or comments on that? Okay, so this is an attractor. We are being attracted to this equilibrium value. And you see, this is in a way painful for us because it means we are stuck to a maximum conversion of 0.32, right? We are not worried about doing anything up here. We don't want to, on balance, produce A. A is our reactant. We want to produce B. So down here is the useful region. And we can't even get to the 0.32 or 0.35, whatever it is, because the rate is reducing all the way along here. And so let's think about that, right? We can see, number one, this blue line is crossing different regions. So first it was somewhere between the green rate and the red rate, if I can call them that. Then as it progressed, then it became more like the red rate. And then it went even below the red rate. It went between the red and the purple. Sorry, by the way, this is actually increasing the rate. So the rate was increasing here. Remember, the high rate region is down here. So we are moving closer to the high rate region. But then we come to a point where we start moving away from the high rate region and we start going to the low rate region again. So the easiest way to understand that or be able to see how that happens is to actually calculate that rate. And of course, we can calculate the rate. So we have available this thing. Actually, this is, or maybe this one, this is a good way to plot it. So let's plot now the rate as a function of all of that. And we have to acknowledge temperature is changing and conversion is changing in both these. So this time now we are looking along that straight line where the conversion is related to the temperature, right? Through the energy balance, we have XA is a function of T. So let's see how this rate is changing along that line. So what we'll do is let's copy all this stuff again. And we do have the conversion as a function of temperature. So let's run a loop again. So for TRI in TR, we are going to recalculate X, and we are going to recalculate, we do need to recalculate our kinetic constants for these different temperatures. Where did we do that? So we recalculate these constants as well, and we have to use the right temperatures. So this is TRI. So the reaction rate RA is, well, it's RA by CA naught. That's actually what we are plotting. So this is equal to KF times 1 minus X. And so the X value is here, so that, and KF. Maybe I don't want to overwrite that earlier KF, so I'll just say KFI, and then minus KRI, and this is times X. So maybe this X I should call XI as well. I and XI. So this is the R value, and what we want to do is store all these R values. So let's just make an array of this, and we'll append all these values into that array. And well, it's an array, so just call it that. So we want to append the scalar value. Okay, so that's what we wanted. This plot now is kind of out of date. This needs to go back. No, that's all okay. That's fine. And then we also want to plot separately. So we need to say figure 2 equals PLT dot figure, and then PLT dot plot. So now we want to plot our rates as a function of the temperature. So the temperatures in the reactor against this set of rates that we've collected. Oh, what is all that? So these rates are fanning out here. What did we? Let's see. Okay, so TR, did I just use TRI? So this shouldn't be a vector of values. Well, XI is a vector of values, that's the problem. So here we want this to be TRI. Yeah. Okay, let's see. Okay, that's better. So we can see here, this has gone far negative now. So let's constrain this one also. So let's call this X2, and let's, or rather X2 equals, so let's just constrain. How did we do it earlier? Yeah. So let's constrain our values for RA to be the positives. So X2 is this plot, and then let's try that. So let's drop the maximum here. 1 is a bit too high. So you can see our reaction rate is doing this. So as the temperature rises, the rate does rise, and then it reaches around, after around 400, it starts to go down again. And we can sort of see that here. You can see as our, so the reaction does progress, then when it reaches around 400, it's starting to move back towards the red here. So remember, that our rates, right, green is a low rate, red is a higher rate, purple is an even higher rate. So we started here, then we started moving towards the red, which is a higher rate. And so the rate kept going up. Then when we reach around here, we are starting to move, we are still increasing, the rate is still increasing here. So the rate increases, and then we reach a point where now we are moving towards the lower rates. So we keep going, and so we get to a low rate region. And then we've constrained the plot here, but if we plot it further, you can see we've gone past equilibrium now, and we are going into the negative side. We are going to the point where we are producing A. So so let's then say, let's stop this somewhere here. So let's look at stopping at around 420 Kelvin instead. So if we change this to 420, where did we T end, right? So we can change this to 420. And now we can see, so it goes up to that point. And still 420 has gone too far. The maximum rate is still somewhere here. But let's not worry about trying to absolutely maximize that just yet. But realize now that this seems to be the best we can do with this one reactor. So maybe you have some suggestions. There are high conversion regions. There are also high rate regions. But we can see they are in conflict with each other now. A high conversion region doesn't mean a high rate region. And so that's the trade-off. And we have to navigate nature. So nature is like this now. So the way nature has set up this reaction, if you want a high rate, you have to have a low conversion. And we knew that anyway. We said this was a problem of the CSTR, that at the high rate regions need a high concentration of A, and here the concentration of A is high. Up here the concentration of A is very low, so the rate is going to be low here, but the conversion is very high, right? So now what if I wanted to get a high conversion? Let's say I wanted to get, let's just say just 60. Can you think of a way to get to a conversion of 60 on this plane? Right? As engineers, we stuck a reactor and the reactor did that. But as engineers, we are free to stick other things into nature and hope for the best, right? So what could you propose here? Any takers for this? Is there a way to get to a much higher conversion region? Anyone going once, going twice? No. Well, what about having two CSTRs and we just cool ourselves back down? So we know that from the first CSTR, we have accomplished a certain something. So with the first CSTR, we've gotten to a certain conversion. So coming out here now, we have this conversion of say 0.25. So there's 0.25, and we still have available the regions up here. So we could simply cool down further here and then let it react again. So we do this, we've gotten here, then we cool down again and then stick another reactor there. So we can just add a cooler here. And so there's a cooler, by that, of course, we mean a heat exchanger. So we put a heat exchanger in between, and then we stick another reactor on here. And now you see we are starting to get to the higher conversion regions. Yeah, we are out of time. If you'll just indulge me a few more seconds here. So this is what we as engineers can do. We can navigate the plane. It doesn't mean we are totally at the mercy of nature now. At least we know about nature. We know nature has this constraint for this reactor, for this reaction. But we can do things. We can add we can add a heat exchanger here. We can add another reactor there. So that's how we can navigate our way through this. So we can get to the high conversions. We do have to acknowledge that the rates in these regions are rather low. So there are low rate regions here. And so if we are going to choose reactors here, even though we might get a small conversion increase, this is likely going to be a very big reactor. It's going to be much bigger than the one here, because for the same conversion difference, at a much lower rate, we need a much greater volume. But we can do that. We can get to here if we want to. Okay, any closing questions or comments there? Okay, and just a note that on this Friday, on this Wednesday, there is a clash with another big university event. So I need to present at that event, so I won't be available for the Wednesday. But of course, we have the Friday slot as well. So we'll meet on Friday instead. So I'll send out an announcement about that, and I'll see you on Friday next. Okay, then that's it for today. Thank you all for coming. See you next time.